Today, lesson 11.4, compound events. We're going to find the probability of mutually exclusive events and find the probability of inclusive events. So remember, a simple event is an event that describes a single outcome. A compound event is an event made up of two or more simple events. And if we have mutually exclusive events, they cannot both happen at the same time, right? For example, right? You can't get an A in this class and a B in this class at the same time, right? You're either going to get one or the other. You can't get both, right? If you flip a coin, you're either going to get a head or a tail. You can't get both, right? It's, the rarity of a coin landing on its edge. So when we think about mutually exclusive events, right, they cannot happen at the same time. So if we look at this Venn diagram here, right, with event A and event B in it, right, there's no interconnection between them. They do not intersect because those two things can never happen at the same time. Right, they're completely separate. So if we have mutually exclusive events, then what we're going to do is add those probabilities. So this says the probability of two mutually exclusive events, A and B, occurring is the sum of their individual probabilities. So this notation here, probability of A, and this is for a union B, for the U there, right, means that it's A or B, okay? So this would be another way of using the word or. So this is the probability. The probability of A or B happening is the probability of A plus the probability of B. Okay? So when a person rolls a number cube, the probability that it's less than 3, well, that's the probability of getting a 1 or the probability of getting a 2. And so I would add those two mutually exclusive events together. All right, so when you see this U here, its union is what it stands for. That means or. So probability of A or B. And so we're going to add those probabilities together. Okay. So a group of students donating blood during the blood drive. Anybody given this Friday? No? Hey Liz, okay, all right. A student has a 9 in 20 probability of having type O blood and a 2/5 probability of having type A blood. Explain why the events type O and type A blood are mutually exclusive. Well, first of all, if you have type O blood, you can't have type A blood. You either have one or the other. You cannot have both, right? Because a person can only have one blood type. So what is the probability the student has type O or type A blood? So these are mutually exclusive because you can't have both. So all we do then is take those two probabilities, 2/5 and 9 over 20, and we add them. All right, so we have the probability of type O union type A, so or, probability of type O or type A. So we add those two probabilities together. So the probability someone has type O or type A blood is 17 out of 20, so it's pretty likely. Right? So it's pretty likely when Hayla gives on Friday that they're going to find that she has one of these types of blood. Do you know which type you have? Okay, all right, O positive. They won't take mine anymore. So. Okay, all right, here you go. All right, inclusive events are events that have one or more outcome in common. So here they show this Venn diagram. How many of you are familiar with Venn diagrams? You've used them before a little bit, okay? All right, so here we have the left side of our Venn diagram here that's in kind of orange is even numbers, 2, 4, and 6. So when I roll a number cube, All right, we get either an even number or we have prime numbers on here, 2, 3, and 5. Right? And since 2 is in both sets of numbers, it's even and it's prime, then it is the intersection between the two. So it's in both of them. Right? So we have even numbers, we have prime numbers, and notice that it says even numbers, and then we've got that U again, but it's upside down with prime numbers. So that means and. Right? So the upside down U means and for intersection. All right? So the U is for union, or the word or, and the upside down one stands for intersection, or we think of it as the word and. So when we have inclusive events, then here we have 3 even numbers plus 3 prime numbers. The only thing is, what happens if I add them together, I count that 2 twice, and so I have to subtract the intersection so that we only count it one time. Otherwise, we're going to count it in both of them, and that wouldn't work. So inclusive events, the probability of 2 inclusive events, A or B, occurring is the sum of their individual probabilities minus the probability of both occurring. So we have probability of A plus the probability of B again, just like with the mutually exclusive, except we have to subtract then the intersection. Anything that's in both groups, we have to subtract those. So the probability of A plus the probability of B minus the probability of A and B, something that's in both of them. All right, so probability even 3, 6 plus probability prime 1, 6, or 3, 6 plus 1 minus 1, 6, because we have one of those that's in both. All right, we get 5, 6. All right, so find the probability on a number cube rolling a 4 or an even number. Now, lots of times these can be done without having to actually make a Venn diagram or all that, and so you can do that also. Well, rolling a 4 or an even number, well, there's 1 4, and then there's how many even numbers? We have 3 of them, okay? And the 4 is included in that, so we just have 3 out of 6, or 1/2. If we look at it using the formula, though, that we would have the probability of a 4 is 1/6, plus the probability of an even number is 3, 6, minus the probability of a number being 4 and even, which is 1, 6. So we still end up with 3, 6, or 1/2 in that situation. All right, letter B says rolling an odd number or a number greater than 2. All right, so let's think about that for a moment. So we want to think about, all right, so we're going to, an odd or greater than 2. So we have the probability of odd plus the probability of greater than 2 minus the probability of anything being both. All right? Well, let's do a Venn diagram here for this. All right? So I'm going to make one. Oops. All right, so we've got 2 circles in. They're going to overlap. All right. So we've got, in here we have odd numbers, so 1, 3, and 5. And then we have numbers greater than 2, right? So the first thing I want to do when I'm doing this is think about what do they have in common, right? So they have odd and greater than 2 would be 3 and 5, right? So 3 and 5 are going to go in the intersection of these two. Right? And if I put the odd ones here on the left, then I have to put a 1 over here on this side. And the greater than 2 on the right, so we have 3, 5, but we also have a 4 and a 6. So the probability of 1 being odd is 3 out of 6, so 1, 3, and a 5. Probability of them being greater than 2 is 4 out of 6, 3, 4, 5, and 6. And then the minus the probability of both, there is 2 out of 6 that is that. So we have to subtract that then. So we get 3, 6 plus 4, 6 minus 2, 6 to get 5, 6. And so the reason that, you think about this, we've got to subtract something, because if I add these two together, I get a number larger than 1. And when it comes to probabilities, you can't have a number larger than 1 for probabilities. You could have 100% of the time it could happen, but that's exactly 1. You can never have a number, anything greater than 1. So you could make a Venn diagram to help you with these situations. All right. All right, so we'll use application problem here, and we're going to use Venn diagrams to work our way through this. Right? So there's 1,560 students are surveyed. 840 were seniors, and 630 read a daily paper. Only 215 of the paper readers were juniors. What is the probability that a student was a senior or read a daily paper? All right, so we've got up here we have seniors are in the green, and paper readers are in the yellow. All right. And then when we put green and yellow together, you get blue, right? Okay. So we have the ones that are paper readers and seniors are going to go in the blue. Right? So we've got to figure out what this is. Right? We need to find the number that go in the overlapping region and to find the number that go in the other two parts. All right. So we need to list. So we need to look at what affects those things. So we have 840 seniors altogether. All right. So let's list the things that we know. All right. So there are 840 seniors, which means that there are, 720 juniors, right? Okay, 840 seniors, 720 juniors. All right. I really don't care about how many juniors there are, but that might help us to determine this. So 720 juniors. Okay. Says only 215 of the paper readers were juniors. All right, so we've got 630 paper readers. So the two big numbers we need are right here, okay? 840 seniors, 630 paper readers, because that's what we're worried about. So this number here in the green is going to be 840. Okay? And in the yellow is 630. Okay, because there's 840 seniors, 630 paper readers. So what we need to find out is then how many people are going to go in here. So it says 215 of the paper readers were juniors. All right. So if there's 630 paper readers, if 215 of them were juniors, how many of them were seniors? 415. Okay, so where does that number go? In the blue. All right, 415 here, because there was 415 seniors that were paper readers. Because there's, I guess this number really didn't matter for us. We didn't need it. Let's get rid of that one. All right. So 215 junior paper readers means that there are 415 senior paper readers. All right, so we need to find these other two numbers then. So 840 minus 415 is going to be 425. Oh, let's make that black. So there's 425 seniors that are not paper readers, okay? And there were 215 paper readers that were not seniors. So to do these, you need to know the totals, which we have 840, 630, and we need to know the intersection, right? And once we know the intersection, then we can put the other two. So, all right, let's find this probability. So we have 1,560, right? People all together. So we want to have the probability that someone is a senior or they read the paper. Okay, remember that the U is or. So we have a probability that someone is a senior plus the probability that they read the paper minus someone who does both. All right, this should be U here. They're senior and they're a paper reader. So we have 840 out of the 1,560 students are seniors. .630 of the 1,560 are paper readers, and 415 people are both. Now, in this situation, all right, what you could do is if you can make the Venn diagram, then really all I need to do is add up those three numbers. Okay, because this 1,055 I got here is just a total of the sum of 425, 415, and 215. Okay. So really, if you can make the Venn diagram, then you can just add those together. Right? So approximately 67.6% of the students are seniors or read the daily paper. All right, so that's where it gets a little tough putting those together. All right, let's see if you can do it with this one then. Okay. All right, recall from lesson 11.2 that the complement of an event with a probability of P, all outcomes that are not in the event, has a probability of 1 minus P. You can use the complement to find the probability of a compound event. So here we have each of 6 students randomly choose a butterfly from a list of 8 types. What is the probability that at least 2 students choose the same butterfly? So that means that either 2 could choose the same butterfly, or 3 could choose the same, or 4 could choose the same, or 5 could choose the same, or 6 could choose the same one. Right? So to do that problem, because we'd have to do 2 and 3 and 4 and 5 and 6 all choosing the same one, a much easier way would be to say, hey, how about if we make it so that we do the complement of that and say 1 minus the probability that they all choose a different one then. Because we know that either they all choose different ones, or 2 choose the same, or 3 choose the same, or 4 choose the same, or 5 choose the same, or 6 choose the same, those things added up are all going to give me the 100% that we're talking about. Right? And so instead of adding 2 and 3 and 4 and 5 and 6 together, we can just do 1 minus the probability that they're all different. So we have to figure out how that works. Right? So the probability of they all choose different would be the number of ways 6 students can choose different butterflies divided by the total number of ways 6 students can choose butterflies. So here we're actually using permutations and combinations in this also. So the number of ways that 6 students can choose different butterflies is going to be a permutation of 8 choose 6. Because order matters. Because once Jake chooses a butterfly, right, that butterfly is taken, right? Then once Jamie chooses one, that one's taken. So it's always going to be, there is order to that because we're specifically given a butterfly to an individual person. Okay. Now the total then is just going to be 8 to the power of 6 because we have, Jake has 8 choices for a butterfly. Jamie has 8 choices. Cody has 8 choices. Molly has 8 choices. Sonia has 8 choices, and Hala has 8 choices. So the number of ways that everybody can choose a different butterfly is a permutation of 8 choose 6 in the numerator and 8 to the 6th power in the denominator. 8 times 8 times 8 times 8 times 8 times 8. Okay. So we find out that value, and then all we have to do is subtract it from 1. So there's a 0.0769 probability that all of us choose a different butterfly. And when I subtract that from 1, I get 0.9231, or about 92.3% chance that at least 2 people are going to choose the same. Right? You know, maybe Jake likes the monarch butterflies and Sonia likes monarch butterflies too, so they're going to both choose the monarchs. I don't know any other types of butterflies, so. Do you, Jake? No. All right, so the biggest thing here is determining what is the, how do I get my number for the, everybody chooses a different one. Okay. And because there was 8 butterflies and we could choose 6, right, that gives us a permutation of 8 choose 6 for the numerator. And the total possible outcomes, everybody has 8 choices. So we have 8 to the 6th power. All right, so let's look at check it out. We'll look at this one together. In one day, 5 different customers bought earrings from the same jewelry store. The store offers 62 different styles. Find the probability that at least 2 customers bought the same style. So here again, we're going to do the probability that at least 2 the same equals 1 minus the probability that they are all different. All right, so we find the probability that they're all different. All right. So let's do the denominator first in this situation. So there's 62 different styles, right? So Halo walks in the store, how many choices do you have for an earring? 62. Okay, she got 62, all right? Sonia walks in, how many choices you got? 62. Molly's got 62, all right? If Cody and Jamie are into wearing earrings, or they're going to get some for their girlfriend, all right, then they have 62 choices also. So this is 62 to the 5th power is going to be our denominator. For the numerator then, all right? So if everybody gets a different one then, okay? Halo walks in the store, she says, all right, I got 62 choices. Great, all right? Now, once she picks one, how many choices does Sonia have now? 61. And Molly has 60. And Cody has 59. And Jamie has 58. Which is just a permutation of 62 choose 5. And then we find that decimal and we subtract it from 1. So we're going to do 1 minus whatever that number is. So let's figure out what it is. So on my calculator then, put a fraction bar. All right, we can do permutation, so we'll do a permutation. Oh, you guys can't do that, can you? Which we can. All right, so we have 62 and we're choosing 5 in the numerator and 62 to the 5th power in the denominator. All right, so there's the probability that everybody chooses a different one. And then we're going to do 1 minus that answer to find the probability that at least 2 people choose a different one. So there's about a 15% chance, 15.2% chance that all the people, or that at least 2 people are going to choose the same one, or 5 out of 31. Really? Let's check that. Math fraction. Nope. All right, must be close to it. Okay. Okay. So we've got inclusive, mutually exclusive events. Inclusive events, when we have, they have shared things, so that you have to make sure that when you add those probabilities, then subtract the one that they have in common, and then a little bit of work on when we have 2 or more, selecting 2 or more objects then. Right?